Let's take a look at section 6.4, optimization problems. And this is part one. We're going to be specifically focusing on creating models for optimization problems. Now, all of this is going to come back together with linear inequalities and give us an example of a type of question that we're able to solve by using linear inequalities. So, already I've mentioned to you that linear inequalities that we've been looking at in the first couple of sections of this chapter are very instrumental in solving something we call an optimization problem. Now, an optimization problem is identified because we're being asked to find the greatest or the least value of something. It could be the revenue or the profit or numbers of things or totals. It can be a variety of things. And sometimes they'll use the word maximum or minimum, but it always is given away because you're being asked to find the most or the least of something. Now, this process is what we call linear programming. And linear programming has a couple of vocabulary words in it that we need to be comfortable with. The quantity that we're being asked to maximize or minimize is referred to as the objective function. It is the objective, it's the function that we are aiming for. And then when we create a system of constraints, the inequalities, we are describing a feasible region or a feasible solution area for the actual question that we're being asked to solve. Now, the best way really to approach these types of questions so you don't get intimidated is to give them a try because they're really not that terrible. So, first of all, a couple of hints which we've already seen in previous lessons, and that is make sure when you're feeling overwhelmed by the many different pieces of information that are coming your direction, always look to the final conclusion or the question. That will help to clarify things for you. And then always pay attention to the numbers and make sure that you stop to consider where they belong. Sometimes they are extra and you don't really need them, but usually they are contributing something to the scenario that you're looking at. Okay, so take a moment, just pause the video and take a look at this question, read it yourself, and then you'll see that I'm starting to put in the steps of how we're going to go about it, approaching something like this. In this one, we actually have a company that makes motorcycles and bicycles, and it talks about how the work area where these vehicles are being made is limited. So we've got some restrictions. No more than 10 motorcycles, no more than 15 bicycles can be made, and no more than 20 of the vehicles of both kinds can be made in one day. They give us some profit numbers, 25 for a motorcycle and 50 for a bicycle. So here's the question. What should be the daily rate of production of both vehicles to maximize the profits? That's what gives it away as being an optimization problem. Step number one, though, define the variables that affect the quantity to be optimized and state its restrictions. If we're going to look at the profit, then the profit's going to depend on the number of motorcycles and the number of bicycles. And so that would be where we start. X is the number of motorcycles, Y is the number of bicycles. And as far as restrictions on those, they really should be whole numbers. They can be a 0 or a 1 or a 2, but fractions don't make sense and negatives don't make sense. Step number two, identify the quantity that's meant to be optimized. And then along with that, you're going to be actually giving an equation, so the objective function. So first of all, the profit is to be optimized. And then when you write the objective function for that, you're going to say that, well, the profit is 25 times x plus 50 times y. The last step that we're going to work on at this stage is to express all the constraints that we see within the problem using linear inequalities, and then we'll graph them. So when it says no more than 10 motorcycles, that means x is less than or equal to 10. No more than 15 bicycles, y is less than or equal to 15. No more than 20 vehicles of both kinds, x plus y is less than or equal to 20. Those are what we call the restraints or constraints on the optimization problem that we're looking at. So let's take those and actually graph them. You're going to see that x is right here in this orange one, and it's smaller than 10 and bigger than the 0. The y is smaller than 15. And then for this one, we have a linear function, where the intercepts are both a 20. And so I've done that, and we're looking for something underneath it. So this particular region that you see is like a trapezoidal one. This is where our feasible solutions would lie. Somewhere in here, the answer to our question is found. And that's as far as we take it at this stage. Let's try one more. Once again, pause the video, have a read the question so you know what's going on, and take a minute this time at each stage to try and answer these questions on your own and see how you make out. So it's about Fred wanting to do an exercise program where he's going to run and swim. And he's got some restraints or constraints on it. He doesn't want to spend more than 12 hours a week for exercising. He wants to burn at least 1,600. It shows us how much you burn for running and how much you burn for swimming. It tells us how much it costs. $1 an hour while swimming costs $2 an hour. Here's your important question. How many hours should he spend at each sport to keep his costs at a minimum? So define the variables that affect the quantity to be optimized and state its restriction well. They're asking us to find the combination which will keep the cost to a minimum. So cost is going to be affected by the hours he spends running and the hours he spends swimming. And so there you have it. Once again, these are whole numbers. Next one, identify the quantity to be optimized. Well, you kind of have to do that in the first step too. It's the cost. And then we're going to put together the objective function so that we can actually see what it would take to figure out the cost. Well, it's 1 times the hours spent running and 2 times the hours spent swimming. So here is your objective function. Lastly, we're being asked to express all the constraints of the problem. And so what do we have? He doesn't want to spend more than 12 hours a week. So x plus y is less than or equal to 12. And then he wants to burn 1,600 calories. So 200 times x plus 400 times y is going to be greater than or equal to 1,600. So there you have 2 constraints. And what they're asking you to do now is to graph them. So you have, first of all, this line, which has, it's going to be using 12 and 12 as its intercepts. This one will have, when we figure out the x-intercept, this is a 0, so we get 8. So you're going to have an 8, there it is right there. And then when you figure out the y-intercept, this one disappears and you get a 4. So you have this little green line. We're going to be doing greater than that one. So you can see that your feasible solution for this particular optimization problem is right in this region here. And that's as far as we go. We don't talk about how we actually find the answer to the question just yet. All right, so that should give you an introduction, and you can get started on trying the following optimization problems. Please notice that I'm only asking you to graph numbers 1 and 4 out of the questions that I'm having you do. So I'm trying to get you to practice the algebra setup and not get too tied down or bogged down with the graphing at this point. Okay, that should be everything. Good luck, everyone.